Hello and welcome to Heybridge Math Department Year 2 Pure Chapter 3 series. Today we're going to be looking at geometric sequences, which is a topic that I think you should find relatively straightforward if you've been following the news at all, because geometric sequences will have come up a lot during the COVID-19 outbreak. Let me give you an example of and let me first of all define what a geometric sequence is. So let's just have a look at geometric sequence. A geometric sequence has a common ratio between consecutive terms. What that means is that you take a number and you keep on multiplying by a different number. So let's give an example and show you what I mean. So let's start off with, say, 3. If we start off with, say, 3 and we multiply that by 2, we get 6. Multiply by 2 again and we get 12. Multiply by 2 and you get 24. This is a geometric sequence. You keep on timesing by 2 and the sequence gets larger and larger. Now if I had, say, 2 people and they had a bug and they passed it on, so that they each passed it on to 2 people, then 4 people would have the bug, and those 4 people would now pass it on to 2 people, so each of those 4 people passes it on to 2 people, so that now 8 and then 16 and the whole world is infected. Now we've seen how the number of times that you pass on disease is or the number of people that you pass the disease on to is really important. Let me give you an example of that. Let's take the same starting number, but say that each person passes it on to 3 people, so that you get 2, 6, 18 and 54. So this is very much linked to the COVID-19 outbreak that we've been under lockdown for this year. But geometric sequences isn't just useful for now, it's useful for always. We can have geometric sequences where, say, let's start off with 100, and this time we're going to times by half. So you get 50 times by half. Again, 25 times by half, and you get 12.5. And we carry on like that. Or we might start off with, say, 300, and this time let's times by minus a third, so that we get minus 100, and we times by minus a third. So this time we're going to get 33 and a third, and we times by minus a third, and we get minus 11 ninths. Don't forget to go back and pause where necessary, making full notes in your book so that you've got clear notes. Take down all of these examples. If you want to create some more examples, now is a good time to do so. I won't tell you to pause always. I'll expect you to do it though as you go along. All right, let's have a look at the general formula for a geometric sequence, the nth term, and it's given as it says there, un equals a r to the n minus 1, where a is the first term and r is the common ratio. So if we had, say, that last sequence previously, or one of the sequences from previously, where we have 3, 6, 12, 24, then if we do, that's like doing, if we use this formula here, we've got 3 times 2, 3 times 2 squared, 3 times 2 cubed. Or if you had, say, the one where we had it going down, you had 100, 50, 25, 12 and a half. Well, that would be like having 100 times a half, 100 times a half squared, 100 times a half cubed. So we can see how it works, the formula does, with some numerical examples. Let's have a look now how we can apply this nth term formula for an example. Okay, so this is taken from the textbook, directly from it. What we've got are 2 sequences, and for each sequence what we have to do is work out the 10th term and the nth term. So let's start off with the straightforward one, the 3, 6, 12, 24. And as you can see from this, the first term, A, is going to be 3. Now the number that it goes up by, which is R, did I mention, by the way? I didn't mention previously that A is the first term and R is a common ratio. So R is the number that you multiply. So if we look at this one here, that's times by 2, times by 2, times by 2. So R here would be 2 and A would be 3. On this one, A would be 100, R would be equal to a half. Right, now that I've corrected my mistake, let's go back and have a look at this. So we've got A equals 3, R equals 2. So the 10th term is 3 times 2 to the 10 minus 1, which is going to be 2 to the 9. Plunking that into my calculator, I get 1536. Have a look at the nth term. Oh, I wish I could write properly. Let's just write that a little bit neater. And just a bit neater. We've got 3 times 2 to the n minus 1. Now I'm going to write this slightly different to the way that the book writes it. And I'm going to do, well, I'm going to leave the 3 as it is for now, but the 2 to the n minus 1 is like doing 2 to the n divided by 2. You could stick that 2 to the n at the end so that you could have 3 over 2 times 2 to the n, and 3 over 2, oh, it's not happening tonight. Let's write that again. 3 over 2 is 1.5 times 2 to the n. How about that? Right, okay, so slightly different to the way the book writes it. And let's have a look at the second example here, where we have, this time in part B, we have A equal to 40, R equal to minus a half. So let's have a look at, first of all, the 10th term. The 10th term is going to be 40A times minus half, which is R to the n minus 1, so it's to the 9, which is going to be minus 5 over 64, apparently. And the nth term, this is where we're going to do 40 times minus the half to the n minus 1. Simplifying a little, we're going to write that as 40 times, oops, I've lost it too much. Now, what I'm going to do here is I'm going to say that that's minus a half to the n over minus a half to the minus 1, because using our rules of indices. Now, minus a half to the minus 1, well, that's going to flip the minus a half, so it's going to go to minus 2, so 40 times minus 2 is going to be minus 80, and we're going to do minus 80 times minus a half to the n. Okay, so what I'd like you to do now is have a go at these questions here. Okay, if you have paused it and you've finished those questions, let's have a look at the answers to this. Now, in part A, we have A equals 4 and R equals 3. So the 10th term is 4 times 3 to the 9. So if I do 4 times 3 to the 9, just sticking this into my calculator, you get 78732. And the nth term is going to be 4 times 3 to the n minus 1. Okay, in part B, you've got A equals 6 to 5, R equals, well, it's minus a fifth, and then the 10th term is going to be 625 times minus a fifth to the 9, apparently, which is minus 1 over 3, 1, 2 to 5. And finally, the nth term which is going to be 625, which is A times minus a fifth to the n minus 1. On both of these, I haven't gone any further and simplified. If you have, good luck. That's fine. As the question didn't specify how it should be written, but it's fine to leave it like that. I guess what we were doing on examples like this here was just showing you one route that you can go down, and if you've simplified it in a way, fine, carry on. If you don't specify and you've got the answer first right, well, you've got it right, great, bang on. I think that's the second time I've said bang on, but on these I didn't bother. Okay, let's have a look at a different example here. So in this example, we have been told two terms from the geometric sequence, this particular geometric sequence, and what we've got to do is work out another term. So we've given the second, we've got the fourth, we've got to work out the 11th. So if you think that AR to the power of 1 would give us the second term because it's it's 2 minus 1, then AR could write 2 minus 1 if I wanted to, or just leave it like that, is going to be equal to 4. And then for the fourth term, you've got a r cubed equals to 8. So if we call that number 1, that number 2, we've got a simultaneous equation. Now you're used to adding and subtracting simultaneous equations, but what we can also do is divide simultaneous equations, and that is exactly what I'm going to do here. We've got 2 unknowns, 2 equations, so we are going to do number 2 divided by number 1. We're going to do ar cubed divided by ar, 8 divided by 4, which is 2, so we have r squared equal to 2. So you have r equals plus or minus the square root of 2. However, the common ratio is positive. So if a common ratio is positive, we just know it's a positive square root here. So now we've done this, we've got to find the 11th term. Well, we've still got to go and find a. By the way, let's use the first equation. So we've got a times root 2 equals 4, so that a equals 2 root 2. Then if you've got a times, if you have to be 11th, then you want ar to the 11 minus 1, which is 10. So you've got a 2 root 2 times root 2 to the 10, which is 64, not Zulane, but 64 root 2. Okay, so there you go. There is how you solve a simultaneous equations 1. Okay, pause, make your notes, and then I'd like you to have a go at this question here. Okay. Right, and if you've had a go at this question here, let's have a look and go through it. So this time we've got the third term of the geometric sequence being 15, so we have a r squared n minus 1 equal to 15, and we've got the 7th, so we've got a r to the 6 equals 135. Dividing 2 by 1, then you have r to the 4 equals 9. 4th root of 9 is going to be root 3. And again, the common ratio is positive. And so we'll just stick with the positive square root. Okay, and now we have to find a. So let's use number 1 again. So we've got a times root 3 squared equal to 15. Root 3 squared is 3. Excuse me. A is going to be 15 divided by 3, which is 5. Then if we want to find the 15th term, we need a r to the n minus 1. So we need 5 times root 3 to the 14, which is 10,935. Okay, give yourself a big tick if you got that one right. Moving on now to another example. I think we're ramping it up in terms of the difficulty. So with this one, we've got the first 3 terms of a geometric sequence. We know that they're all positive. What we want to do is find out the value of x. Now, if we have, for part A, if we need to find the value of x, we know that we start off with our first number, 3, and we times 3 by some common ratio, r, and that gives us x. And then if we take x and we times it by r, we get x plus 6. Okay, so we can make an equation, or two equations from what we've got here. We've got 3 lots of r equals x, and xr equals x plus 6. Now, there's too many unknowns, too much going on here, so let's do some simplifying. Why don't we say from this equation here, r equals x over 3, and then we could substitute it into that equation there, so that you get x times x over 3 equals x plus 6. Nova Book goes about it in a slightly different manner, and it's probably quicker. It's just I think mine is more explanatory. It's easier to understand my method. So here you get x squared. Well, I would say that, wouldn't I? Now I'm going to bring that 3 up there, so I want to get 3x plus 18. So now we have x squared minus 3x minus 18 equal to 0. Factorising that out, you get x plus 3, x minus 6. So x equals 6. It does not equal minus 3 because back here we said the 3 terms were positive and x therefore must be positive. Okay, now the question also says, what does the question say? The value of x. Boom, done that. Part B, from a 10th value of the sequence. So if we said that r was x over 3, then r is equal to 2. So if we want the 10th, part B, we want 3 times 2 to the 9, which is 1536, apparently, according to my notes there. Right, okay. What I would like you to do is I'd like you to pause, make notes, of course, on this here. Just make notes on each little bit here, scrolling through so you've got it all there. And then can you have a go at that example there, please? Right. Okay, so in this example, we have, like we had last time, we'll say that r is 3 over x, like we did previously, because if you had xr equal to have I done that right? So 3, I think I might have done that the wrong way round, haven't I? Should we ad lib? Yeah. We've got, on this occasion, I've done that the wrong way round, haven't I? Because r is going to be x over 3, and then what else have we got? Then we've got also that r would be equal to 9 over x, and then we can say that x over 3 equals 9 over x. I've gone about it a slightly different way to the way that I did last time. I hope that's okay. We're going to end up with x squared equal to 27, and that leaves us with x equal to 3 root 3. So there you go. Kind of makes sense when you look at the sequence here. Okay, we're just going to find the fourth term here. So let's find that by doing a, which is 3 times well, we need to find out r, so that's going to be 3 root 3 over 3 to the 3. So the 3's will cancel, so you'll get 20s. What will you get? So you've got 3 times root 3 cubed, which is going to be 9. Root 3 got there in the end. Okay, so now let's have a go at a different example again, ramping it up one more time. Oh, by the way, if you got that first time, give yourself a big tick, make some corrections like I've just had to, and let's move on to the last example here. Okay, so this time we've got a geometric progression, geometric sequence, a geometric progression, GP for short is the same as a geometric sequence. It means the same thing. What we want to know is which term does the first term happen to be above 1,000,000? So if we look at this here, we see that A equals 3, R equals 2, and using our familiar formula now, we've got 3 times 2 to the n minus 1, and we want it to be bigger than 1,000,000. So there is 1,000,000, and we have 2 to the n minus 1 is bigger than 1,000,000 over 3. Now, for some reason, I didn't pay too much attention, but I was looking at the book earlier, and I think they used some weird base for this. What I'm going to use is I'm going to use ln. I'm going to use natural logs, so I am going to go log 2 to the n minus 1 is bigger than log 1,000,000 over 3. Of course, it doesn't matter what base I'm using, this n minus 1 can come down in front, so you get log 2 is bigger than log 1,000,000 over 3. Then we can divide through, so we can go n minus 1 is bigger than log 1,000,000 over 3, all divided by log 2. Horrible calculation to do, but we have calculators in this modern world. So we have n minus 1 is bigger than 18.3, so n is bigger than 19.3, so we're talking about the 20th term in Bob's Your Uncle. Okay, can you have a go now? Or copy down this, of course, into your notes if you haven't done so already. Copy this down here, slowly going through so you can see it, and then have a go at this. Okay, and this one you have A equal to 3, R equal to 4 again, so you have 3 times 4 to the n minus 1 bigger than 1,000,000, and therefore that's 4 to the n minus 1 is bigger than 1,000,000 over 3 again. Like 1,000,000 in these examples, and dividing it by 3 for some reason. Okay, so it's the same pattern, it's almost identical to the last example that we did. We'll take logs. I'm just going to skip a step here because I am hardcore. So n minus 1 log 4 is log a million over 3, so you've got n minus 1 log all divided by log 4. And if you work that out, apparently you get n minus 1 is bigger than 19.2. Oh, sorry, 9.2. So n is bigger than 10.2. And we're talking about the 11th term. Okay, so there you go. Could you now give yourself a big tick, correct, obviously, if you haven't done so already. And then we'd like you to have a go at exercise 3C. Off you go. So let's just write that down. Shall we write down exercise 3C? Thank you very much.